Walter, you're back now.
Yes.
And you're giving a talk with 30 minutes assigned to it on small-scale processes in atmospheric ocean modeling, etc. Yeah?
That's a long title, but
that's fine.
Creating stochastic surrogates for the small-scale processes to define atmospheric ocean models. I'm rather new to this field. I have an aerospace background, so most of the work that I'll be discussing, or a large part of it, is done by dynamical students. So credit where credit is due. Well, I too have a picture like this. You've seen quite a few of them already. Right? Of course, ocean and atmosphere is a multiscale system. Right? You have the x-axis, the length scale in meters, and horizontal time scale in seconds. And the lowest scale is just the turbulence, the atmosphere. If you move up the scales, you find things like thermals, storms, cloud clusters. If you move up even further, at some point you're at planetary length scale, so you can't go any bigger. You can still go up in time though. And if you follow this all the way up, you get to the top, which is the climate variation. So clearly, resolving this entire system on a computer is simply impossible. You go from meters to planetary length scales, and from seconds all the way up to centuries. So let's say if we're interested in climate variation, you're going to have to model a large chunk of the system. Right? Well, I guess you will recognize this picture from the proposal. So on the left we have a climate model. I believe it has about 10 to the power 5 cells on the horizontal direction, so on the surface. And each of these cells is roughly in the order of tens or 100 by 100 kilometers. So that it leaves plenty of space for cloud formation inside a single cell. And even though these clouds are subcell, they're quite important and affect a big unknown in climate prediction. So depending on how high these clouds form in the atmosphere, they can either trap the heat when they're low, or if they're very high, they can have a net cooling effect or reflecting somewhere back into space. So you need to take them into account somehow. And in this work on the CWI, what they've done at certain strategically placed locations, they've done LES simulation inside the non-living cells. So I'm pretty sure most of you know LES, right? It's technically still a model, but in the case of atmospheric models, it's considered to be very high resolution. Right? You resolve a lot of the clouds and you just model the small scale turbulence. So it's a high fidelity model, and as such it's also a very expensive model, and it has a different time step than the global climate model. Right? So with a single global time step, you have to run this model a bunch of times, and then only at certain time intervals can you exchange information between the LES and the climate model. So I think the climate model gets average further profiles back from the LES, and the LES gets its boundary conditions, its force intervals from the climate model. So it's this cyclic system that solves that works. So this is an example of that. So each of these boxes is an LES simulation, 3D, so you have the top view. Over here you can see the time step of the LES, which increases much more faster than the time step of the background global model. Each box is independent of the other, so it's a fully periodic simulation, each individual LES. But because each one gets its boundary conditions from the global model, they all kind of force in the same direction. So it almost looks like one big cloud system that is compact. But as I said, these things are very expensive. Each is an LES simulation. And so what they've done here is they've placed them basically over Holland, where they also have some mythological data that they can use to compare. But you have 10 to the power 5 of these cells, so it's impossible to do LES for all of them. So it would be advantageous if we could somehow replace these LES simulations and data driven stochastic testing. Well, this just summarizes basically what I said before. We have some core scale model, but actually interestingly could be a weather prediction, could be a climate model, which depends on some range of some scales. And in the game we're playing at CWI is we do run the full model, but only for a limited amount of time or only for a small spatial location. So this builds up a database of both large and small scale solutions that we use to build this surrogate. So how you build the surrogate is dependent upon the relation that your grid size has with your small scale data point. So you can ignore the ones on the left and just focus on these. These are the small scale. And so if you're in this particular zone, which is called the stochastic zones, you might have some large scale grid cell that has a few data points, few small scale data points, and others are quite well seeded. So within itself there's quite a lot of uncertainty about the small scale. So in this case, it might make sense to create a stochastic surrogate with small scales. If on the other hand you have a lot of data points in each cell, you might know enough about the small scales in order to make a deterministic surrogate. And so in general, we have some PDE, which depends on, in this case, this is the velocity field next to the field, and the small scales tend to appear as a source term on the right hand side. Like this. In case of velocity, this will be like a one-source transfer or something like that. And we either don't have no first principles for B, or if it's just too expensive to run it efficiently. And so this is the approach we follow. We can run the full scale system for a limited amount of time, which we use to create some stochastic model. And we couple this to the coarse scale model in a two-way fashion, and then we run the recording for a cheap model with the stochastic surrogate. And so, in general, the framework that Dan has developed with the students for this problem is to replace this subunit scale source term with some stochastic process for each large scale node xi, and then we model this as a conditional transition probability. So the probability of B at the next time step is dependent upon the observed values of the previous time step. And then the form of this PDE is somehow inferred from the available data. So this leads to this type PDE. This has climate model, this has weather model, which is coupled to a network of stochastic processes. Could be a market chain where you only have dependence on previous time step, but this conception you can build in a large history if you want. So to illustrate this graphically, well, now the large scales of the node Q, which is generally denoted in vorticity instead of velocity. But if you have a deterministic model for B, you get something like this. But in reality, there are many B's which will be compatible with the same large scale state. So this provides maybe an argument to the model in a stochastic fashion. And what we do is for a large scale grid point xi, we again run the model for a time, we collect small scale data for every grid point, and then we somehow use this data to resample B, given a observed large scale state. And that's in general procedure, and there are many methods that actually fit within this thing. I'll skip the details. As an example, I'll consider mostly 2D non-divergent flow, so that's flow at a constant density of water, so it's an ocean model. It's basically 2D Navier space, but expressed in the case of stream function and logistic Q. You have some approximate wind force and some approximate Coriolis force to make an ocean model. But the interesting part for us is J term, Jacobian, which is it's just a non-linear reflection. It's just a non-linear term that will couple the small and large scales. And so we can't resolve this thing entirely, so you coarse grain it, so if you have some, let's say if you're doing an LES, you have some convolution with a special filter. In this case you get a Q bar instead of a Q. And if you apply this to the governing equations, you get the exact same equation, but with the addition of a subcascading source with B. And well, because J, the coding, it doesn't commute with the convolution. And so the convolution of J is not the same as J of the convoluted quantities. So this is not zero, and that's basically what happens. And we're going to model B in a certain way. We have basically a list of demands that we would like to have. I already mentioned it's stochastic. It has to be correlated to time and space, preferably. And especially space is tricky. You have these large flow fields, so modeling correlation of that can be quite hard. We want to be conditioned on resolved variables, because the actual B is also dependent on both large and small scale, so we want to surrogate to have this as well. And in absence of the best case, the detail is small, data inferred, and the surrogate has to be pre-computed, so this might take quite some time to sample it, but once we have that, it has to be cheap to run. And another very important thing is we want this stochastic surrogate to extrapolate well. Right? And that's also a very difficult thing. We have some data over certain time periods, and I've tried a bunch of different methods to do this, and it's not that hard to create a good model which represents the data with all these demands in place. But really, when you move much beyond the data and you start to predict for long time periods, getting all this in place is very difficult. Well, there's basic sketches where I've told us already. We have some observations, we have some conditional probability, or some market optimism. Skip that. So our goal is the exact Coarse model. Not the same as a full model, so this is still a Coarse model, but this B term is computed with the exact Q. So this is the best possible model that we can hope for. We don't have that. We have some approximated form which I can local utility. So we have some PDE with B tilde, where B tilde comes from this conditional resampling strategy. And well, if you just run these models side by side and start to compare these fields for Q bar, and you're giving them the same initial conditions, so they're pretty good in the beginning, but at some point they won't diverge, they will not look the same. And we don't really care about that, because we're interested in like climate, so what we really want to get right is the model climate, so the climate of this thing. So for instance, if you have total energy in the system, scale up, you would like to get the statistics, so PDE or moments of the energy is the thing we want to get right with this model. We have some results from a paper done by Nick van Hol at CWI. It's a string function, and it's the statistics, so you have the time mean over here, of the actual full model, and a standard deviation. And on the right you see a stochastic resampling of that model. Which is the formula that I said before. So this is basically what I talked about. People over a long time and statistical quantities of that. You can see that they match pretty well. Also, if you look at other statistics like autocorrelation functions, so the lines are the actual model, the symbols are the stochastic estimate point. And again, it matches quite well. But the thing that was done over here is because on this western boundary, you can see the most activity occurs. So the coupling between the large and small scales, let's say, was only considered along this boundary over here. So it's not really a full field model in this case. And if you do that, this is what I do over here. So now I do consider the full entire field. So then this becomes very high dimensional. And you also get correlations in time and space. So as an example, again, it's simple, let's say, a toy example of an ocean floor. This is the Q bar, so the best possible model, and this is the subject's filter. This is called the eddy force. It's basically any part of the Jacobian that contains some result skills. And in order to see what this looks like, so this is the full model, and that's the thing we're trying to model. And you can see it's almost like a living thing. It's clearly affected somehow, but it's a very finely grained structure of those skills. And so it's quite hard to resample something like this, given only access to this data. There's not enough correlation to reliably resample something like this, because this has such a fine-grained structure. Conditioning on coarse gains variables is very challenging. So if you do that, it's very easy to lose spatial correlation. As I said before, you start to resample it, and you pre-tilde it. You don't tend to get something nice like this, but something very, very noisy. And while this is still the ultimate goal I have, and I have some ideas of how I might do this, but as an initial step, what I've done is, instead of this full difficult eddy forcing of observing, a simpler sourcing. And so you could think of, for instance, this linear difference over here. So now B is just the full field vorticity, so the high fidelity vorticity data projected onto the core scale, so that's just Q bar minus the models, which is the Q tilde. So why would you do this? So you could think of this as, for instance, like a posterior correction term upon your modeled Q tilde. And you could also think of this when you multiply this difference with an inverse time scale, you can add it to the right hand side of your momentum equation. And in that case, it becomes a linear relaxation source there, which tends to push Q tilde in the direction of Q bar. It's like a simple correction technique. It's not going to be as good as the actual B. It's not going to be as good as the eddy forcing. But at least now I have a B, which is going to correlate fairly well with something I actually have access to when I'm on model. It's just the linear difference between Q bar and Q tilde. So if I have Q tilde, this tends to correlate pretty well with what I know. And just as an example, this movie again. You can ignore the top, you can ignore this guy. So this over here is, I'm sorry for the change in notation, and this is B, so the actual B, so this is the linear difference between the high fidelity and the low fidelity vorticity fields. And this is a data-driven estimate of that, given only access to the Q tilde. And anyway, if you stare at it long enough, you will see that it's fairly similar. Certain structures are resolved in both velocity fields. For instance, these dark blue dots appear here as well. And in general, it behaves quite similarly to the actual data. So what I built is to say that in the movie, what you actually see over here is a sort of a mean field. And for each large scale Q, I basically take the mean of all possible values I have. And what Dan did before was take a stochastic surrogate. So then, given some large scale state, randomly pick one of these beats. But in that case, you again get a noisy field. So if I take a mean, I get something which has a nice correlated structure. Right? It doesn't look noisy. And if I would have to do this in a stochastic fashion, I mean I have a 128 or 128 grids, so I would have to estimate the covariance matrix, which is 128 squared or 128 squared. It's a very difficult problem. if I just take the mean and basically get the correlation for free. But it's now deterministic. It's no longer a stochastic surrogate. But I could do the same thing for the standard deviation. I have a bunch of samples for each bin. I could also use this transport standard deviation. And that's what I do here. So this is a similar type of delta term, only not with this, but this is a difference between the stream function. This is the data-driven estimate. At some point you see people start to correlate pretty well with the true data, high fidelity data. But I can also transport a standard deviation of this guy at the same time. So I could add this to that in order to get the time-dependent error box on this part. I also look at an even simpler alternative B term. In this case, no longer even a difference, it's just tau times Q tau. You might think, well, why would you do that? But if you remember the goal, let's say I want to approximate the first moment of the energy, the actual energy, compared to what I actually moment, I want to make this as close to zero as possible. And maybe for this goal I don't need the actual energy force, maybe something simpler will just suffice. But if I with like a physics-informed approach, I can, given Q and given stream function, I can derive an energy equation. I can do this for tau 0, I could also do this for this equation. And then I find that there's an additional source term in the energy equation. Just 2 times tau times the energy that I have access to. And so the effect of adding this to the verticity equation is that it adds either a production or dissipation term in the energy equation. And so if this tau is negative, then it tends to destroy energy. If it's larger than 0, create energy. And so I can extract this tau from my high fidelity data. In this case, I get the scalar time series. And the problem is with this, I no longer have to do it with full field reconstruction, but I have to represent this scalar time series in order to meet this goal as good as I can. So if I do that, so the blue line that you see over here is the true energy of the full scale simulation. If I set tau to 0, so if I just do the unparameterized model, so no data driven model whatsoever, I get the red line. And since I give them the same initial condition, it's very good in the beginning, but as time moves on, this guy will start to look differently from the truth. And if you integrate this long enough for years, then you'll end up with different statistics. But if I add this simple data-driven term, I get the line in green. So this line you see here, which is not perfect, it's just a simple source one, but at least it looks more like the actual energy. And so I can extract a training set for this tau, that you see over here. And this is as far as I've gotten up to this point. So my next step would be to create a model for this tau, training on this data. So maybe some algorithm type model in order to estimate this, and then plug it back into the Coarse model and run it for a long time and see what the statistics are. And so this is actually my last slide, and I'll end with some references and take any questions.